So one of the defining features of machine learning, as the name suggests, is that the machine learns how to perform a task, and it does so without concrete human input on how it should be performing that task. And this is something that I touched on in the previous video. But how exactly does the machine learn? What does that learning process look like? That's what I'm going to cover in this video. The first thing to say is that there are a lot of different approaches that different machine learning algorithms can take to this process of learning. And it depends largely on the type of task that you're trying to perform. But there are some common approaches and more popular ones, and I'll go into those in a bit more detail. So what are the different types of tasks that we can perform with machine learning algorithms? Fundamentally, a machine learning algorithm, and a way to look at it, is that we are taking inputs and we are getting outputs. So the input might be a chest x-ray, and the output will be, is there a pneumonia, is there a cancer, or is it normal chest x-ray? The input might be a series of blood tests and a series of vital signs, and the output might be, what is the risk of this patient clinically deteriorating? Or the input could be a video of a patient with suspected Parkinson's disease, and the output would be whether or not the algorithm thinks that they have Parkinson's disease. But really the types of inputs that we have and the type of outputs that we're interested in can vary quite a lot. And depending on the type of output and type of input that we have, the type of tasks have different names. So for example, if the outputs are specific categories or classes, and we already know what classes we want to sort them into, then this is called a classification task. So the example of chest x-rays would be a classification task. We want to know, is it a pneumonia? That's one class. Is it a normal chest x-ray? Has it got cancer? Or sometimes you can have multiple classes being present at the same time. But overall, this is called a classification task, and we have a number of different classification techniques that we can use for that. If instead the output is not a class, but it's a value that we're trying to predict, then this is what's called a regression problem. So let's say we're trying to predict how long someone's going to be in hospital, or maybe what their life expectancy is. In those cases, the outputs that we're trying to give, they're all numerical values, and therefore that's a regression problem. And again, there's a whole host of different techniques that we can use for regression. Sometimes you're trying to do a classification task, but you don't know what the classes are. And in that case, you want the algorithm to find those classes for you. And this approach is called clustering. So we don't tell it what the classes are before, and we ask it to try and find what are some sensible classes within the data that we give to it. And again, there's a whole host of clustering techniques, and they have their own mechanisms of learning as well. There are other methods as well. I'm not going to go into them in detail here because they're generally less applicable to medicine. A vast majority of things are in this kind of area of classification, as well as some uses of kind of regression and clustering as well. So within each of these types of tasks, you have multiple different algorithms that can perform them, and some of those algorithms will have their own specific mechanisms for learning, whereas other ones will kind of share common mechanisms. And so if we look, for example, at classification mechanisms, then some common classifiers are support vector machines, neural networks, k-nearest neighbors, logistic regression, naive Bayes, and random forest. And within those, some of those will have their own mechanisms of learning. So for example, k-nearest neighbors does, random forest does, naive Bayes does, but the other ones, logistic regression, support vector machines, neural networks, they all use a kind of shared learning approach, which is something called gradient descent. And gradient descent is a really kind of fundamental principle for a lot of the really exciting areas of machine learning, and a lot of this whole area of deep learning that we've seen recently and has kind of led to this newfound excitement in medicine. And it also demonstrates a lot of the principles about how these learning mechanisms take place. So I'm going to dive into a bit more detail into this whole gradient descent process, and work through a few examples just to give you some kind of concrete intuition about how this works. And in terms of all those techniques that I listed, it's not essential probably at this stage to go into great detail into those, but I would recommend if you are thinking about going really deep into machine learning or kind of exploring it further, then it is worth just understanding what all those techniques are, and kind of getting a better intuition about that. And in one of the later videos, I'll be sharing some really good resources that you can use to learn what these different techniques are and kind of gradually build up a bit of a picture of what machine learning is and what techniques you need to know and that sort of thing. So if we look back at a definition of machine learning, which I shared in the previous video, we can see that there's fundamentally several different elements to this. So firstly, we need to define what our task is, and that's something that we do. That's kind of where the human input comes. We need to decide what type of machine learning algorithm we're going to use, although sometimes in practice you'll actually just try multiple different ones and see their performance. But essentially, in order to quantify it, you do need to pick an algorithm. We'll define what a performance metric is going to be, because that enables us to actually measure how well it's doing, and update it and improve it. And then finally, we'll feed the data in and we'll use the kind of performance metric to continually improve the algorithm until we're getting the best performance that we can. So I'm just going to kind of summarize this quite neatly in this little table, and we'll use that for reference kind of throughout these examples. So the first example is going to be a relatively kind of simple example, and all the examples I'm going to give are going to be slightly contrived, but it's just to demonstrate what the key principles are. So if we're trying to predict someone's body surface area from their height, then we might want to train a model to do this. So task, okay, we're trying to predict the body surface area. Before we go on to these next stages, let's visualize the data. So we have, let's say, about 20 or so samples. We have their height and we have their body surface area. And if we look at this data, we can see that it looks like probably the relationship is what we'd call linear. As one goes up, the other one goes up, and it does so in a kind of fashion that could be fitted with a straight line. So therefore the algorithm that we might use is, technical term is linear regression, but essentially this involves finding a best fit line that will fit to our data. And as a kind of brief maths refresher, you may well remember that y equals mx plus c is just the graph for a straight line. So we're going to try and find this graph with the values for m and the values for c that will best fit through our data. The two variables that we're going to be changing in this model is m and is c. So m being the gradient, c being the intersect on the y. We also then have the performance. The way that we'll measure this is we'll look at the error of those guesses and we will square them. So if we, let's say for example, had this best fit line and these were our points, the error is this green segment. And what we're going to do is we're going to take each of them, we're going to square them, and then we're going to add those all up, and that's going to be our total amount of error. We're then going to perform this learning, and we're going to demonstrate using this gradient descent approach to do this. And the way that gradient descent works is you have those parameters, you have m and c, and you're going to try and optimize those parameters. But what you do before that, or kind of before you optimize it, is you have to take a random guess for both values. In this case, we're going to say c is 0, and actually we're not going to train the model on that just for simplicity. So we're going to say the only parameter we're trying to optimize is m. And initially the algorithm will just make a completely random guess. And let's say in this case, it looks like it's guessed m is about 0.25. So for every one it goes across, it goes 0.25 up. And we can see it doesn't perform particularly well at this point. And if we quantify the error by drawing these lines, and if you imagine lines from every single point, I didn't just draw them, mostly just could take too long. But if you imagine all of these lines, you take them all, you square them all, and then you add them all up, then that will be our overall amount of error. And you can see that there's a lot of room for improvement on this graph. So at the moment, the line is not doing a fantastic job. But then what happens in machine learning in this gradient descent approach is you'll plot that error on a graph. And here we have the gradient around 0.25, and the error is currently 11. And that's a somewhat arbitrary value. What the algorithm will then do is it will look, okay, if I went downwards with the gradient, or if I went upwards with the gradient, if I made the value a little bit higher or a little bit lower, then what would happen? In which direction would it improve? And in this case, if we look back at our graph, we can see we want our gradient to be steeper. So we want our line to be coming a bit more up here. And the algorithm is smart. It looks at this and it can see that. So it says, okay, we want a steeper gradient. So it knows to change this gradient value higher up. And then what it does is it will plot this gradient. It can't see the red line. We can see that as a kind of template, but it can see this gradient, this black dotted line, and it will go, okay, so I can see that it goes down, the error goes down in that direction, so it will take a step in that direction. And then it would step down, let's say, to around here. So now the gradient is about just under 1, and then this gradient lifts up on this side. And basically, it just repeats this process. So again, it looks here, it looks at what is the error, so it will calculate all these different points between these points and between this line. It will square those, it will sum those up, and it will plot them on this graph. Again, it can't see the red line, we can see that, but it can see this black dotted line. So it can still see, it just wants to know which way should I jump, and it knows I should still be jumping in this way. So then it'll take another jump and it'll get to here, and again the black line is lifted up again, and it will jump again, and it will just keep on jumping, and then eventually it'll get to this point where the black fit is, the best fit line is doing a pretty good job, it's going through most of the points, and at that point it can see that its gradient is pretty flat and it's not going to take very big jumps. So it's just going to kind of hover around this area until it's finished training, and then that's going to be the final model. So now we have this model, which is this black line, and as I said, models are about taking inputs and outputs. So the input would be the height of a new person, and then the output would be the body surface area. So let's say someone is 0.5 meters tall, and I guess we're talking about kind of kids or babies here, because that's not particularly tall. But let's say someone's 0.5 meters tall, then we would look at this graph, this best fit line, and we would say that they're probably going to be about 0.9 meters squared body surface area, and that would be the final prediction of that model. As I said, obviously this is a very simple, contrived example, but that is how this principle would work. So that's a regression example because we're trying to predict a specific value. So it's not a classification example, which is where we're trying to predict a specific class. So let's now go through a classification example. So in this classification example, we're going to try and predict whether a skin lesion is cancerous based on its diameter and based on the consistency of its pigmentation. So again, the task is to classify skin cancer or not. We then have this graph, and we can plot these kind of cancerous points and these benign points, and we want to identify this decision boundary that separates the two. So whereas before in linear regression we were trying to find the best fit line, now it's a classification task, we want to find the kind of the separating line that divides the two. And the technical term for this one, previously we used linear regression, this time we're using logistic regression. Again, I wouldn't worry too much about the name at this point, but this is just a common, quite simple classification mechanism that we can use, and it would work well in this case. So the difference here is that it's a decision boundary rather than a best fit line, as I said. So there's an error function. The error function is a little bit more complicated here, so I'm not going to go into detail on that. It's a similar sort of principle with regression. We're just looking at how well is it doing at the task, and it will look at which points are classified wrong. So if we have a decision boundary that's, let's say, here, then there's going to be a lot of points that are on the wrong side of the decision boundary, and then they'll all contribute to the error function, and they'll just make it be a higher value if you're having more and more errors. And then, okay, we're going to use gradient descent to learn it, to demonstrate that principle. So same sort of approach. Although this time our point is starting as a negative gradient. And yeah, exactly the same principle. We start with a random guess. We then quantify the performance, so we can see that it is classifying some of the cancerous ones on this side, but it's also getting a lot of cancerous ones in the not cancerous, and that would all lead to error measures. So we're getting a decent amount of error here. And again, we're just going to take a guess and try and improve. So as we take this guess and then things get better, we're going to continually improving our guess here. We're continually finding that we're getting better and better performance, and it's exactly the same principle. So then eventually you'll get to this point where you have your best fit line. And then when you get a new mole, then you will, or a new skin lesion, you'll see its diameter, you'll see its pigmentation coefficient, which is something you can kind of calculate based on the image, hypothetically, and then you'll be able to see, well, it's over here, so I predict that it's going to be cancerous, or it's over here, I predict it's not going to be cancerous, for example. And then as a final example, if we're predicting the length of stay, let's say based on someone's age and the number of medications, and of course it's a very contrived example, you're not really going to try and do this, particularly with a model as simple as this, but let's say we have 5 data points. We have 5 examples of patients, we have their age, we have the number of medications that they were on before they had an operation, and we had how long they stayed in hospital. And we wanted to train a model to fit that. Then again, to find our task, predict the length of stay based on the age and number of medications. And this time we're going to use a slightly more complicated algorithm. We're just going to add in this extra kind of variable. We have essentially this parameter, which is A, when multiplying it by the age. We have this one, which is B, multiplying it times the meds. And of course, this type of task is a regression task because we're trying to predict the length of stay, which is a number, it's a numerical value. So this is similar to the y equals mx plus c example, but rather than m times x, we've got A times age and B times meds. So the two parameters that we're going to optimize are A and B. We're going to again use a linear regression, and we're going to learn by using this gradient descent mechanism just to demonstrate this. So first step, to take a random guess of A equals 0.5, B equals 0.1. So this would be our algorithm, is predicting the length of stay is 0.5 times age plus 0.1 times meds. This is our data points, and then we look at the predictions and we can see that it's doing pretty badly. Like all of these predictions are pretty far out. So lo and behold, this doesn't work particularly well as a algorithm, at least not yet. And again, we'd quantify the error here. So we would look at the prediction and we look at the actual and we would subtract them. So 44.8 times minus 10.1, square that, do that for all of these points, sum that up, and that gives us that error. And if we imagine that kind of curve, we can see our error is actually pretty high at this moment. So then what we do is the algorithm will look, okay, which direction should I change? And it sees that for A, it should decrease it, and for B, it should increase it. Then we look and we see, the predictions are a little bit better. I mean, they're still definitely not great. So we'd quantify that error again and then loop over the whole thing again. So keep on updating it. A is keep on going smaller, B keeps on going bigger. And then eventually we end up with this algorithm, which is A equals 0.1, B equals 0.5. And when we look at the performance, actually it does a pretty decent job. Like all of these predictions are fairly close. And of course, I fixed these data points so that it would do that. There's almost no chance that this would work in real life, but this model is now giving the best performance that it could give. So then if we had a new person, we knew their age, we knew number of medications that they were on, we could have a decent go at predicting the length of stay, assuming that this worked. And now, of course, all these are quite contrived examples and they're not things we're actually doing, and these aren't contributing to the hype that we're seeing in medicine because no one's making models like this. But the key point is that it demonstrates this principle of gradient descent, which is that you take a guess, you look at which direction to update the parameters, and you keep on updating it in little steps until you get to the best performance. And the reason why this technique is so popular and is being used in so many of the algorithms that we're using today is because in order to find the best parameters straight away is very difficult and very computationally expensive, because if you have all these data points and you're trying to find the best model, you'd have to analyze them all simultaneously and find this best model that fits all of them. And that's like very, very difficult to do, and it requires very large amounts of computation. And because we just don't have the computers to be able to do that, and we want to analyze really large data sets, we need to take a different approach. And what gradient descent enables is that at each point, we're only doing a simple computation. So we're either updating it, making the guess, and then we're quantifying the error of the guess. Then we're updating it, and then we're quantifying the error. And because we're doing it in stages, the amount of computational power that we need is never as big as if we tried to solve it all in one go. And that's why this whole deep learning approach, which involves very large amounts of data, it's enabled by this mechanism because we don't have to try and solve the whole thing all in one go. And that, it turns out, works pretty well actually for a lot of tasks in gradually updating and getting to this best points. Now, as I said, these are all quite simple examples, but there are some reasons why things are a lot more complicated. One of these is that the relationship is very rarely linear. In most cases, you will not be able to fit a best fit line. And actually, if you were able to fit a best fit line, then you wouldn't really need machine learning approaches. You could probably just solve that using kind of traditional statistical techniques. There's also a lot more dimensions involved. All the examples I did were kind of 2-dimensional. In reality, you might have 100 dimensions or 1,000 dimensions. So things kind of scale up quite quickly. We can visualize up to 3 dimensions, but once you get beyond that, it's quite hard for us to visualize that. Although there is a joke that Geoffrey Hinton, one of the kind of founders of deep learning, is able to visualize in 10 dimensions or something. But I think for us mere mortals, we can't visualize in more than 3 dimensions. And these models are 100 dimensions, 1,000 dimensions. Another thing is that these error graphs, they're very rarely as simple as this. So I showed some ones that were kind of nice simple curves. Actually, the kind of pattern is often a lot more complicated, and you have all these little dips and kind of hills and that sort of thing. So again, it's a challenge trying to take the guesses that get you to the absolute lowest point all over, rather than just maybe like a little local point that's quite low, or somewhere else that's actually not the best point to find. So that's another technical challenge. And another challenge is making sure that your model is not fitted to noise, that it's actually fitting to kind of true relationship that will then apply if you take that model into the real world. Because one thing that can happen, and it's a term called overfitting, which I'll talk about in some of the later videos, is that your model will work really well on your data set, but it's fitted to the noise. So then when you try and apply it to a new data set, it's not going to work particularly well. And this is obviously something that is very important in medicine. We don't want to have a model that's not going to work when we come to actually apply it to the real world. So as I said, while gradient descent underlies a lot of these approaches, there are other algorithms which have their own mechanisms of learning. I'm not going to go into detail on those here because just time restraints. I don't want to make this too long a video. One I would recommend looking up was k-means clustering, and I'll leave a link in the description to a great video that explains that. All those algorithms, so the classification algorithms that I mentioned, a lot of those will also have their own mechanisms. So I would recommend, if you're interested, have a look at those and kind of understand how that process works. And what's interesting about some of these other techniques is that there are some parallels with the gradient descent approach. Often these other techniques will also involve making guesses and then kind of gradually improving those and using some sort of error function that you're then trying to find the lowest value for, and again find the best fit of inputs to outputs. As you look at these other mechanisms, you'll probably see some common threads between those as well. So one other thing I just want to cover before we wrap up with this video, and that's the distinction between supervised learning and unsupervised learning. So in supervised learning, we know what the outputs that we are trying to get are. So for example, if it's a classification problem, we know that the classes are pneumonia, normal chest x-ray, rib fracture, coarctation of the aorta, or whatever. Or if it's a regression problem, we know that we're trying to predict the length of stay in days, or we're trying to predict the life expectancy in years. Those are all tasks where we know what our output is. And those regression classification are examples of supervised learning algorithms. You also have these other approaches which are called unsupervised learning. And basically in unsupervised learning, you don't know what the specific output you're trying to predict are, and you're asking the algorithm to try and identify the kind of structure within this data and some potential classes that it thinks make sense. So for example, you might give the algorithm data about people with heart failure, and you might give them their BMI, their blood pressure, their various different like blood measurements like BNP, and all these different factors that are relevant for heart failure. And then you would ask the algorithm to find some clusters within that and understand what are the types of, maybe subtypes within these population of heart failure. And it might be the case that the algorithm will then identify that you have a subtype where it's predominantly people with high BMI and high systolic blood pressure. You might find another subgroup where it's low BMI, but it's high BNP, for example. Or maybe you have another one where it's old age and you have a high systolic blood pressure and a high diastolic blood pressure, for example. And an analogy that's often used is that you have supervised learning is like teaching with a teacher. So you're teaching the algorithm, but you're giving it kind of feedback on what its predictions are, whereas unsupervised learning is you're teaching without a teacher. So you're kind of giving it the data and you're asking it to go away and find its kind of this inherent structure within it, but you're not giving it that direct feedback in that moment. And with the gradient descent approach, the types of algorithms that use this are supervised learning. In order for it to calculate that error and then update itself, it needs to be able to assess its performance. And the way that it does that is by comparing what we tell it are the outputs versus how it predicted the outputs to be. And it wouldn't be able to do that if we weren't giving it those outputs. So that's why it has to be supervised learning. And supervised learning is the area of medicine where we're seeing the majority of papers and the majority of interesting research being done at the moment. There are some unsupervised learning applications, such as identifying subtypes within different diseases or subtypes based on different drug responses. But the vast majority are in this area of supervised learning, and the majority of those are also in the area of deep learning, particularly looking at things like images. So in this video, we've seen that there are a lot of different algorithms within machine learning, and some of those have kind of common approaches to learning, such as gradient descent, and some of them have their own specific mechanisms of learning that are specific to that algorithm. Gradient descent is the mechanism that underlies most of the excitement in healthcare at the moment. It's led to this ability to perform deep learning and perform really interesting complex tasks. Gradient descent involves making a guess, quantifying the error of that performance, and then continually improving that guess until you have the best performance overall. And we've talked about supervised and unsupervised learning, and how supervised learning is where we give it the outputs and we are teaching with a teacher, whereas unsupervised learning is where we don't, so there's no teacher to train the algorithm. In the next few videos, we're going to talk about neural networks and deep learning, what exactly they are, how they work, and why this is so interesting for healthcare.